and gentlemen, good morning. It's a pleasure to welcome you to our lecture series, AI in Science and Engineering. And the title of today couldn't fit better to our lecture series, the role of academia in the study of AI. I think we all would like to know how to cope with the pressure from the big tech pros down to politicians asking us what we should, which model to use and which data center to build up, and do we need regulation, do we don't need regulation, and at the very end, how does the whole thing work? Why does it work? Does it work in all cases, and what is the situation we as humans have still in our hands? And I guess we hear more about that, but we hear it also on a more foundational, mathematical foundational level. Our guest today, Shahar Mendelson, is very well known for his mathematical foundational work in the area of artificial intelligence and data science. In all the areas of multidimensionality, geometry, he has done really seminal work where he's very well known for. He is, for example, he got the medal of the Australian Academy of Australian Society of Mathematics. He is a member of the Australian Academy of Science. He was professor at Technion. He is now at Texas A&M. And I'm really very happy to have you here. And we are very much looking forward to your presentation. Thank you.
So it's a pleasure to be here. And I don't think I will have answers to the question that Gerti asked. I have many more questions than answers. And in fact, when I was invited to come and give this talk, the one really good thing about talks like that is that it forces you to think about what it is that we do and what's the role of academia in general, specifically in this changing world. And this world is changing faster than I could have imagined. As I told Gerti before the talk, I have friends who are senior people working for Google and OpenAI and NVIDIA, and we all agreed that had someone told us 3 years ago that we would be where we are today, we would have said, no, you're joking, it's impossible. And yet here we are. So I started thinking, while preparing this talk, what is it that we're supposed to do in academia? And I'm sorry that I start with philosophy rather than with mathematics. But for me, the role of academia is simple and complex at the same time. It's the promotion and preservation of understanding. And the crucial thing for me is to distinguish between understanding and knowledge. They're not the same thing. Now, knowledge is extremely important. You can't get to understanding without knowing first. But knowledge is easier, it's faster. And I can tell you as a mathematician that I've proved several results during my career that when I proved them, I didn't understand them. It took me several years of thinking more and more about them, and then you finally get a deeper understanding of what's going on. And I think that this is what we need to do in academia. And just to quote Michel Talleyrand, who's an Abel Prize winner, that was from his Abel Prize interview. Understanding is a slow process, and that's I think that that's what we're here for. Now, there's a basic question of, okay, why don't we have a theory of AI? I mean, we don't. And it's not clear why. Well, it starts with the following thing. A long time ago, when I started my career, I was a student, neural networks were extremely important. They were the main topic in machine learning at that time, and we thought that we understood them pretty well. Today, in hindsight, I can say we didn't. But the object that we were studying looked like this. This was a basic neural network, and I don't know if you know this book. This book was very popular at the time. It's from '99. It was written by Martin Anthony and Peter Bartlett. And this is the sort of object that we do understand. Again, today I would say not as well as we should have, but we do understand. But this is what we're dealing with today. This is sort of, not even today, this is maybe from, well, Transformers was 2017, I think, so 8 years ago. We're not even remotely close to understanding what's going on. And I'll try to explain why and what I think we should be doing. But this is why we don't have a theory of AI. Now, some people would say, okay, why do we need a theory of AI? Is it just an intellectual exercise? And I would say no, for two reasons. First of all, it will take such a huge role in our lives, and personally, I don't want something with such an important role that we don't understand. Okay, but that's just me. If you want something more practical, this is, I think, the most important point. The progress that we see today is mainly technological. I don't think that there were any what I would call substantial breakthroughs in AI, but hyperscaling, which gets us where we are, is technological and amazing intuition. I mean, the people who actually run applications do things that are, in my opinion, unbelievable. But what happens if this technological progress stalls, if we can't go to the next step, if we can't hyperscale even further? Okay, so that's why I think we need a theory of AI, which leads me to the question, who will develop this theory of AI? The two obvious candidates are the tech giants, but while I think they find the theory of AI interesting, a little because of this reason, it's not their main focus. It's not their main focus now, and it's unlikely to be their main focus in the next few years. At least that's what my inside information sources also tell me. And the other alternative is us. And I think that this is precisely the type of problems that we in academia were expected to deal with. I mean, it's a fundamental question, hugely important, calls for long-term investment of time and resources, and the chances of success are not clear. It's speculative, cutting-edge research. If I remember correctly, the ERC, that's sort of their title. This is what we're meant to do. So if you ask me who's supposed to develop the theory of AI, it's us. Okay? I'm sure that some people would disagree with that, but that's my position. How would you develop the theory of AI? Well, it's an incredibly non-trivial challenge, because the way I like to see a good, let's call it research group, if you want to call it, it's like a chain. At one end, you have a mathematician, someone who proves theorems, etc. At the other end, you have someone who writes code or tell a large language model how to write the code that we care about. Now, all the two ends can't communicate, really, because they don't speak the same language. They don't understand each other. And in between, you have statisticians, computer scientists, engineers. Their input is essential. I mean, every part of this chain is every link is essential, every link affects all the other links, and there's a huge language barrier that one has to overcome. And I discovered this, personal experience, I think it was maybe 12 years ago. A colleague from electrical engineering, so theory of electrical engineering, not that far away from mathematics, came to me about a question. She wanted me to get interested in phase retrieval, sparse phase retrieval. And the person who asked her the question was from physics. He was a physicist working with lasers. He had a lab with lasers, and that was the motivation. So first of all, I had to communicate with electrical engineering, and it took us time. And I finally understood sort of what she wanted me to do. And then I came to the next meeting with a formulation of a statement based on certain assumptions. And I told her, okay, would that work? And she said, no, 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 no. These are lasers. Lasers don't work that way. And I had to reformulate the version of the problem, the mathematical formulation, about 4 times. All the formulations were almost equivalent from a mathematical perspective, but only the last one would have had any practical impact as far as the end user, in this case, the physicist, was concerned. So without that input, I would have had a nice mathematical problem, I would have enjoyed solving it, and the impact of it would have been completely negligible, other than a theorem in mathematics. So I know that when a mathematician says we're developing a theory, I want to develop a theory of AI, the natural suspicion would be it would end up as being a thick book with a lot of theorems that no one would care about. That's not what I have in mind. Now, to convince you, if you're not convinced by now, because I know that many of you work in the area, so you know this as well as I do, that this is an incredibly non-trivial challenge. I want to start with a toy example. Okay, so a classification problem, and I took my son's toys, and he loves construction vehicles, and the question is, can you identify which is a bulldozer and which is an excavator? But it's just an example of a classification problem. But the idea is that you show a machine a bunch of photos, and based on giving the machine labels, so saying this is a bulldozer, this is an excavator, and sometimes even you make mistakes, the machine will be able to guess correctly on the next photo that it's shown. Okay? But what does it mean from a mathematical perspective, from not just a mathematical perspective? What do you really have to do? Well, the first thing is you need to represent every picture in a way you can work with, right? That gives you a 0-1 valued function, say 0 for bulldozers, 1 for excavators, okay? This function is incredibly complex. What you want to do is you want to try to approximate it from using a simpler object that comes from a function class. So you have the choice of the function class you want to work with. This too is a collection of simpler binary valued functions, and you have to decide on the notion of what is an error and what is the price of making an error. Okay? Once you have that, you have the approximation error of the problem. So you fix a function class and you fix a way of measuring the error. It says, okay, the best in the class can do this well. Then you need to choose a statistical procedure. Okay, you get a random data, pictures and labels, and you need to use a statistical procedure to choose a statistical procedure, and that determines the statistical error. And the goal is that the statistical error would be as small as possible, getting you closer to the best in the class. Okay, and then finally you need to implement this procedure. You need to actually run it. And there's a computational aspect, and there is actually algorithmic aspect, just even beyond the mere computational cost, etc. Now, as you can see, this is a toy example. It has multiple facets. Every choice affects everything, all the other choices. For example, if I take a small class, so the star, say that the star represents the true 0-1 function. If I choose the purple blob as my function class, I get an approximation error, okay? The statistical error will be smaller because the class is smaller, okay? And probably running the search within it would be easier. If I increase my function class, I decrease the approximation error, but increase the statistical error. And if I go even bigger, I get to a problem that's called overfitting, right? I might choose a binary function that is too rich. So every choice affects everything else, and this is in a toy example. And we're talking about something that's way, way, way more complex. Okay, so that's what I've said. The targets are complicated. Each component is comes from a different world. All of them affect all the others, and philosophically, bigger is not better. I mean, taking a bigger function class doesn't mean that automatically you'll get better results. And the reason that I'm mentioning this is because we're talking about hyperscale in neural networks, and say that we get a technological progress and go from the current level of what we can do to the next level, it doesn't automatically mean that things will become easier, right? And I will say a few words about that in a second. Okay, so this is why I think that this is the right picture, even in the toy example. Now, where we are now, as far as neural networks or large language models, the networks are huge. Their architecture is incredibly difficult, and huge is, as far as I can guess today, it's 10 to the 12, 10 to the 13 parameters. We know that neural networks are universal in the sense that if you take a neural network that's big enough, it can approximate every reasonable function. But we don't have really a quantitative theory. The quantitative theory that was developed in the late 90s said, well, if the function is smooth in that way, then you can do the following thing. But this is irrelevant as far as the functions that we're trying to approximate now. It's incredibly difficult to describe them, let alone to understand how they are approximated by the networks we care about. Now, on the one hand, we can get data that's reasonably cheap. In the olden days, the restriction, and I'm sorry I'm saying the olden days, not that old, but in the olden days, one of the constraints was that data was really expensive. So you had to deal with that. In some of the problems we're interested today, data is not that expensive. In the biotech world, this is false, but still. Now, thanks to technological progress, we can train neural networks on something like 15 times the number of parameters that are used. And the really interesting thing is that you have linear scaling, that you can actually get good results if you have a data set that's 20 times the number of parameters. Another thing that's strange, and I'll explain a little later why it's strange, is that you don't stop at zero training error. To get the right result and to get linear scaling, you need to go beyond the zero training error, which is meaningful. And another part of the game that's non-trivial is that the data that you have is not independent. And a lot of the theory, the statistical theory that I will talk about today, is based on the assumption that the data that you get is independent. Okay, now, if we want to go further, there are various options. Wait for the next technological progress, which either will or will not happen. Okay, understand what we do today in a better way, so get a better understanding of the approximation, statistical, and computational aspects using the same technological constraints that we have now. And for me, the dream, but this is really a dream, it's not something that we're remotely close to, is to be able to scale down rather than scale up. So the cost of hyperscale is immense, and it's not going to get cheaper probably. The number of players who can afford really the full-scale large language models are governments and tech giants. I don't think that a university can afford that. And it would be amazing if, thanks to better understanding, we'll be able to deal with less complex objects but still get the same type of performance. But for that, we really need to understand what's going on, and at this point, we don't. Okay, what we do have is a list of rather remarkable questions. Each one of them is an exciting challenge. Each one worth, in my opinion, investing in effort. So the first question is, what happens if we scale up, if we can scale up? The fact that we see a certain performance today at this level doesn't mean that if we go to the next scale, we will see the same sort of progress. So if we scale up, what will happen to the approximation error? Will we see linear scaling? Now, linear scaling is something that, so linear scaling from my perspective is, I need to give you a proportional number of data points, proportional to the number of parameters that you have, to get a good statistical performance. Okay? Linear scaling is something you would expect to see in linear models. Proving that even for linear models was difficult. It was open until maybe 10 years ago. To do it for simple, not simple, but problems that like covariance estimation, we only knew how to do that 5 years ago. I mean, have a theorem. And here we're talking about a highly nonlinear model. So there is no reason to expect that we will have linear scaling. And the reason that we see it is completely obscure. My personal suspicion is that actually the complexity of the class of functions corresponding to a set of parameters is much more than linear, but then you have a phenomena that's like benign overfitting that allows you to perform well even with a linear number of measurements. But we're not even remotely close to understanding this. Okay? But nothing promises us that if we go to a higher scale that the linear scaling law would continue. If it doesn't, we could have serious overfitting issues. Now there's the optimization aspect. The problems are not convex. We're likely to be converging to a local minimum. Why is that good enough? It is, but why? And another question, for me, a big elephant in the room, is this really dependent on the neural network architecture? Or will we be able to get similar performance with different classes of functions? And simple answer is, I don't know. Okay? Now, I'm going to tell you a story about, the development of, for me, the most interesting question in statistical learning theory over the years. And it's close, maybe it is a good starting point to trying to understand the linear scaling problem. Okay? Maybe. But I want you to keep in mind that this is a starting point, nothing more than that. It's a complete answer to a question, but the question is probably much simpler than what we have to answer. Because here, even in the simpler neural networks that were around 25 years ago, they're still incredibly complicated objects that we don't really understand. And also the data is not IID, and the theory that I'm going to present is completely IID. Okay? So here goes. This is a classical statistical learning problem. And in the statistical learning problem, you have a given class of functions. Okay, you know the class of functions. There is an unknown target that I denote by y. You know the class of functions, but you don't know the distribution that generates the data that you will see. And the goal is to try to use the random information, the random sample that you get, to identify or get close to the best function in the class. And the best function in the class, in this slide, I wrote it in the sense of the squared loss. Now, the theory that I'm going to describe only for the squared loss, but it goes well beyond it, okay? And also, people sometimes think that this theory is only true for when the class is convex. That's false. you don't need convexity, you really need to assume very little on the class of functions. Okay, so that's the problem. And the question is, you give me the accuracy that you want. Okay, how close you want to be to the best in the class. And how sure you are, which means with what probability you want to ensure that you're that close. How many sample points do you need to see to ensure that? Okay, to get a random choice after I see the sample, I choose a function, say in my class, and I want to guarantee that the error, the deviation from its performance to the best in the class, is at most epsilon with probability 1 minus delta. How many sample points do I need to do that? That's the question. Okay? Now, the point is, and this is a surprising, really surprising fact that I noticed maybe 25 years ago, that this problem is actually a question in high-dimensional geometry. And I'll explain why. Now, the results that I will tell you about are optimal statistical bounds, which means I give you an arbitrary class of functions, or minimal assumptions. I will tell you how many sample points you need, okay? And it will match the lower bound, and the lower bound is something that's called minimax. So somehow it's the, if you need this number of sample points to ensure that you do well for any target which belongs to a trivial class of targets. And trivial in this case are realizable, so zero error, or additive Gaussian noise. That's the, so from a statistical perspective, that's as well as you can hope to do. Now, at the same time, the optimal solution will involve a procedure or procedures that are totally non-feasible. So from a computational perspective, you know, if I show this to someone who actually has to run algorithms, he will laugh in my face. Okay, so there is another deep fundamental question of whether there is a trade-off between statistical optimality and computational optimality that we don't understand. I'm going to talk about the statistical facet, but to get a real solution, a workable solution, we need to understand that part as well, and also the approximation theoretical side. Okay. Now, in all this type of statistical problems, there's one issue. There is some phenomenon that is true in the real world, and the question is, can we see that phenomenon where all the information that you have at your disposal is the random sample? In this case, you're looking for the true minimizer, the best function in your class. The fact that it's the true minimizer means that the risk, which is the expectation of f of x minus y squared, the risk of every other function in the class is bigger than the risk of the minimizer. So you know that for any function in the class, this inequality is true. But the question is, can you exhibit that using the random sample? That's the question. Because once you see, if I can show that for some function, this inequality holds, then that function is not the minimizer, and I can exclude it. Okay? Now, the two big elephants in the room is that you need to do this exhibiting uniformly in the class, and also you need to be able to do it without knowing the identity of f star, of the best in the class. So somehow I need to be able to compare, but doing that without knowing the object that I'm comparing to. Okay? Now, the easy way out, and that was the way people have done things for a long, long time, was to run empirical minimization. Empirical minimization simply means pick the function in your class that best fits the given data. Okay? I will explain why this is a problematic choice, but philosophically, the reason that ERM fits this model is you know that the empirical risk of the minimizer will be negative because the best in the class is one of the competitors. So actually what you want to exhibit is to say, okay, if I have a positive empirical error, then necessarily the risk would be positive, and therefore I'm not a minimizer. That's somehow the philosophy of how ERM fits the model, and that's how ERM algorithms are analyzed. Okay. So then you want to ask yourself, I want to understand the sample complexity. Let's start speculating what the answer should be. Okay? And the idea is that because you don't have all the information, right, you just see a sample, you can make mistakes. And you need your sample big enough to make sure that when you make a mistake, the mistake isn't too bad. So here are two types of mistakes. One mistake is this: if you're really close, if you look at functions that are really close to the true minimizer, they look just like it. They're not very far from it. So on the sample, they're likely to look almost the same, right? And therefore, you can make mistakes because of that. So somehow you need to measure the complexity of your class of functions close to the minimizer, because and show that if you're not very, very close, you will be able to show that. Next, there is the interaction with noise. If the problem is noisy, and you move, even if you move away from the true minimizer, their interaction with noise could mislead you and cause you to make mistakes. So you expect that there's an intrinsic factor, what happens close to the minimizer, that will have absolutely nothing to do with the target or with the noise level, and one that calibrates the level of the noise. Okay, so this was a sort of a working hypothesis that's been around way before I joined this game. We were able to show that that was true even in, not fully, 10 years ago, maybe. Okay, statistical learning started in the late 60s. Okay, so just to give you a perspective of how difficult it is. So again, this is the picture, right? The closer y is to the blue blob, which is the function class, the problem has less noise, and you would expect the intrinsic factor to be dominant. The further y is, you will have, because of interactions that y has with functions that are further away, any algorithm is potentially will make mistakes, and you need something to calibrate that. The other conjecture, which seems maybe also too optimistic, is that the sample complexity has a special form. So even if you take it for granted that there is an intrinsic factor and an external factor, okay, you can say, okay, I need a sample big enough to overcome both of these. That will be the sample complexity. The other conjecture is even a bit wilder. They say, okay, I want to solve the problem with probability 0.9. Okay, I want to get a sample big enough that would allow me to do that. How many more sample points do I need to add to get it with the probability that I really care about? 1 minus delta. And the crazy conjecture is that you need a trivial number of points to go beyond the constant probability level. So there is an intrinsic factor, an external factor, both at a constant probability level, and then if you go beyond just a bit, noise level squared divided by epsilon times log 1 over delta, that's enough. Okay? So even if you believe this, and this was a conjecture, by the way, it is true, it's no longer a conjecture, even if you believe that, you need to understand, okay, what happens at the constant confidence level? What are these, threshold sample complexities? How are they reflected by the structure of F, et cetera, et cetera, et cetera? So here's a short history of statistical learning theory from the 60s to about 15 years ago. At every step of the way, people looked at richer and richer problems. In the beginning, because the people working in statistical learning were mainly from computer science, they were interested in binary valued problems. Classes that are binary valued, the target that's binary valued, etc., etc. Then, thanks to some mathematical progress, significant mathematical progress, people were able to move from binary valued to uniformly bounded. Okay, it's much more difficult, but still, it's hardly general. Now, the two interesting comments about this thing. When I gave talks at statistics seminars in the early 2000s about that was the state of the art in the bounded framework. It's a result that I have with Peter Bartlett and Olivier Bousquet, both of whom now work for industry, senior people in industry. There was always a statistician in the audience that would say, okay, that's really cute. Can you deal with Gaussian noise? And of course, because the framework was bounded, the answer was no. And he said, okay, come and see me when you know how to deal with Gaussian noise. Before that, this is not interesting. You had two communities working on almost identical problems, but they weren't willing to talk to one another. Right? So I'm well familiar with that challenge. The other, actually more interesting thing, I gave a talk about the best result that we had in the bounded framework, and a professor of electrical engineering came to me and said, look, this is really interesting, but I've run experiments, simulations, and we can get similar results in heavy-tailed scenarios. Can you explain that? And I didn't believe him. And I went back to his lab, and he showed me the experiments. And he was right. He got the right results in heavy-tailed situations. And I went like that. Said, okay. And then it was clear to me that there is a big chunk of the theory that we're missing. Right? Because not only didn't I know how to do that, I couldn't believe that the theory could be extended to deal with a heavy-tailed situation. Now, there was something that I missed in his experiments. All of his experiments were in either realizable case, low noise case, etc., etc. Now, foolishly, I ignored that, and I worked for maybe 7 years trying to extend the theory that we had for the bounded framework to sub-Gaussian. That means that all the random variables that you have decay, have nicely decaying tails, better than Gaussians. But it was clear to me that the theory that I had couldn't go beyond that. And the gap between sub-Gaussian and heavy-tailed is like this. It's like a different world. But in all these cases, what would happen was this. They took 10 to 20 years to resolve. They involved the development of a sophisticated mathematical machinery. They all used empirical risk minimization. They all did this idea of excluding functions by exhibiting the fact that the risk was positive. It was based on somehow balancing notions of complexity of the class with concentration phenomenon. And the thing is that if you go beyond that, you go beyond the sub-Gaussian case, even slightly, not totally heavy-tailed, not only did the theory didn't work well, but ERM failed. Okay? It's not that the theory couldn't prove that ERM doesn't work, ERM doesn't work. Okay? With one important case where it's not true, I'll get to that in a minute, but in any case, like it or not, the real world is heavy-tailed. So ERM doesn't work in general. The one caveat was low noise problems. And that's exactly what I was shown in that lab, and I totally ignored that because I didn't know what I was looking for. Perhaps I should have spent more time talking to them and seeing the simulations that they run. So just to explain why low noise problems are different, are somehow much easier. So let's look at no noise problems. And in no noise problems, y and f star are the same. Okay, so y is an element in your class. And ERM would choose any function in your class that agrees with y on the given data. So f of you choose any function f for which f of xi is yi. And the point is, the analysis of RAM would say, if f is far away from f star, then that should be seen because the two vectors can't look alike. F of x star can't look like the vector yi that you're given. Now, here's the next slides are the only piece of real mathematics I'll talk about in this lecture, but it's such a beautiful thing that I didn't want not to say it. So here's something that I missed, or all the education that I got in mathematics, we missed this point. Say that I want to show that the empirical square, so you take a function, raise it to the power 2, and take the empirical mean. I want to show that this empirical mean is not too big, versus I want to show that this empirical mean is not too small. So the way we used to do it is to prove a two-sided inequality. But actually, that's the wrong way of doing it, because there are two inequalities, showing that it's not too big and showing that it's not too small. Now, if you have one unreasonably large data point, in statistics we call it an outlier, it will destroy the upper bound and only help you in the lower bound. Okay? And the thing is that the phenomena that you want to prove an upper bound is totally different from the lower bound, and the lower bound is the one that we care about, because we want to say that to exhibit the fact that f minus f star is big from the random data that we get. It's a different phenomenon. It has nothing to do with tails. It has something to do with not being too close to zero. And but on the other hand, once you have noise, you do need the upper bound for the analysis of ERM. And that's why ERM fails in heavy-tailed problems. That's where the outliers kick in. So a few years ago, I developed what I call the small wall method. And it gives you precisely what you want. You can show that if you are bigger than the intrinsic sample complexity of the class, then with extremely high probability, f minus f star xi on a large number of points will be very big. Therefore, the two vectors will not look alike at all. And in fact, it will do so in a stable way. So the vectors are not just different on one coordinate, they will be different noticeably on a proportional number of coordinates. Okay, and that's why you can make things work even with various notions of malicious noise. Okay, but problems have noise. What happens then? Well, a few years ago, Gabor Lugosi and I developed what we call the median of means tournaments, and that solved the problem. It exhibits the positive risk uniformly in the class and without knowing the identity of the best in the class. It leads to exactly the conjectured complexity, and I know that I haven't told you what the intrinsic and external sample complexities are. And unfortunately, the procedure is totally useless. So you can't run it. It's a statistical procedure. It's not a procedure that you can actually run on and get a practical result. So what are those mysterious intrinsic and external sample complexities? Well, they're governed by something that's called the local Rademacher complexities. And I'm not going to tell you what they are. I will quickly run the formulas. Intuitively, and it's best to think about it intuitively because these are really highly complicated objects. What you have is you're given the sample, you have a class of vectors associated with the random sample, and the intrinsic sample complexity is measured using the degree of correlation this set has with some sort of standard noise, and the standard noise is just a random vector with minus ones and ones. Okay? This is sort of it measures the complexity, the oscillation of a certain random process, but intuitively, it's how rich your class is and how well it's correlated with this notion of noise. Whereas the external sample complexity is governed by a slightly different oscillation function, and it measures the correlation with a different random vector, and that random vector is sort of sine times the noise. Okay, that's the big picture. I don't want to get into more details. They're incredibly non-trivial mathematical objects. Trying to analyze them, getting bounds on them from above, from below, is a highly non-trivial problem. Okay, but this work led to proving that the conjecture was right. The intrinsic and external sample complexities are given using fixed points of these two strange-looking oscillation functions. The result was wonderful in the sense that it improved all the known sample complexity. All the state of the art was given using that. And actually, in many cases, the upper bound was equivalent to a theoretical lower bound. Okay, so when we did that, that was the two papers, one by myself and one with Gabor. They were out there maybe 5 years ago. We really thought that that was it. Okay, that was the end of the story. However, there was another lower bound. And the lower bound was, in some cases, substantially smaller than these upper bounds. Now, intuitively, and again, I don't even want to write what the lower bound was, but intuitively, the lower bound is the sample complexity that you need had the problem been Gaussian. Okay, I know that it's not always well defined, but that's sort of an intuitive description of what that lower bound is. Now, the reason I liked it was that it explained, or it and geometry exhibited the lower bound in the following sense. At that level, you can show that, in the Gaussian setup, you can show that if you take your function class and restrict it to the given data, it hides a canonical structure, in this case, a large Euclidean ball. And once you know that, then for almost trivial reasons, you know that no algorithm can perform, in a better way than what this lower bound said. It somehow says, inside your object, there is hidden like a nugget of evil that prevents you from doing any better. Okay, so I like that. I like that lower bound. But, that's where we were. We had the upper bound. We had this lower bound. The upper bound was sharp in many cases, but there were cases where this lower bound, there was a big gap between the two. Okay? And I believed up to a year ago that what was loose was the lower bound, and I worked really hard to prove that the lower bound was loose, and I was wrong. What was loose was the upper bound. And it turns out, and this is a joint work with Danny Bartle, is that if you add one minor assumption on your class, then the upper bound can be improved. And intuitively, the right sample complexity is believe that your problem is Gaussian. That's the right sample complexity. But the algorithm is totally not computationally friendly. Okay? In the Gaussian case, you could run ERM. It would work well. But to get the Gaussian type of performance in the general setup, I don't know how to do that in any reasonable way. Okay. There is a very, very, very long way to go, even though we have satisfactory theory in this perspective. We still have a huge way to go. First of all, in real-world problems, the data is not IID. So we need to develop a theory that would be able to deal with a non-IID setup. The classes of functions that we care about are really complicated. So even if I have the right complexity parameter, telling you what that complexity is for a function class that's really difficult is it's a problem by itself. It's like describing something I don't understand in terms of another thing that I don't understand. It's not like a huge step forward. So linear scaling, even in the case of really basic neural networks, we don't have a satisfactory theory to explain that. Maybe benign overfitting, which we sort of understand in linear regression, but we're very far from getting it even in the simple neural networks. And finally, there's the question of feasibility, that the algorithms that we have in the heavy-tail case, they're not feasible. And we don't know whether this is something fundamental, that there is a gap between statistical optimality and computational optimality. If there is a trade-off between the two, we should understand it, because then we will be able to choose how to calibrate. Different scenarios might call from, if the data is expensive, we might go for statistical optimality, smaller sample size. If computation is expensive, the other way. So, but we need to understand this trade-off before we can start playing with it. Which brings me back to the climbing metaphor. The problems are interlaced, and every aspect affects every other aspect. And here, all this work, which isn't enough even to explain the statistical setup in real-world problems, was just on that, the statistical setup. I didn't talk about how it affects all the other components, and the reason I didn't talk about it is because I don't know. Okay? And we need to try to figure that one out. Now, if we want to understand, to develop a theory of AI, one of the most important things is to do it in a collaborative effort with industry. And the reason is this: if you want a physics metaphor, they are experimentalists, and they have all the data, and we need to understand, and we need to talk to them, because they have remarkable intuition on what works and what doesn't work. And the more we talk to them, maybe we will get sort of a hint of where we want to start climbing, right? For me, because I come from statistical learning, the question of linear scaling was the most exciting. Someone coming from optimization would look at a completely different aspect. But in any case, they run experiments, large-scale experiments, on a day-to-day basis, and not talking to them is just foolish, right, in my opinion. The other thing is that we need to talk to each other, because, as I said, working on each one of these aspects separately is nice, it's satisfying, but it won't get us to a theory of AI, because we're ignoring all the other components, and the other components are essential. And the last thing is how we train our students. And I'm not going to talk about how to incorporate AI in academia. I'm talking about training the next generation of AI researchers and practitioners. And for me, we need to train them to be multilingual. We need for them to be able to understand the way multiple disciplines, researchers from multiple disciplines, think, and their language, and what they find interesting, and where the core challenges. And we tried doing something like that about 15 years ago when I was still at Technion, and we brought together friends from different departments, trying to build a curriculum for precisely that. And everyone, and I want to emphasize, everyone in the room, we were all friends. And we all wanted this to work. And 10 minutes after we started, people got into arguments because everyone said that it is inconceivable that students could graduate without knowing X. And everyone had their favorite X. So unless we wanted to have a degree that would take 10 years instead of 3 or 4 years, and we couldn't make it work. I think that today it will be easier to make it work because people understand how important it is. That was less clear 12, 15 years ago. But it would also involve us, I'm talking about myself, for being more flexible and saying, okay, my X is really important, but there's a bigger picture that we have to think about. And that's already, how should I say, it's a cultural and a psychological question that is, other than doing my best, I don't know how to answer, I don't know how to solve it. But anyway, I think that we have to, our role in academia is to lead. We're not leading at the moment, and we should. And that's all I have to say. Thank you.
Thank you very much for your presentation. We have talked about multilinguality before, and he didn't change the slide. I didn't know that that's the last line of your slide of your presentation. Questions from the audience?
Hello, thanks for the talk. When moving the theory from IID to real-world data, is there a good argument why the IID theory might help? Or could it be a completely different approach which...
Okay, so a while back, as I mentioned, I got interested in sparse recovery and phase retrieval and problems like that. And over there was a period where people were, maybe they still are, interested in structured sampling. Instead of IID, you would get measurements generated by non-IID matrices, but that had some special structure like circulant, Fourier, etc. And our starting point, whenever we tried to understand why it worked, was that it really worked, right? Which is a huge advantage. I mean, you know that if you dig in that place and you work hard enough, then you will hit gold. I didn't say this during the talk, but or didn't emphasize it enough. For me, the core feature in the IID sampling is that a certain set, and let me get to that set, this set has a special structure, okay? And the whole game, the whole analysis, I didn't prove anything, but the whole analysis would say, understand the geometry of that set. Once you understand the geometry, the sample complexity estimate follows. And IID implies that the set has a certain structure. Now, if you have a sample complexity that's the same as in the IID case, then it stands to reason that the geometry of this set in the IID and the non-IID case should look alike. Proving that is much harder, but it's true, okay? You're asking me if there isn't a complete, maybe there are venues where you have a completely, crazy way of sampling, in which case you still have, I don't know. But I would start with this. I would start with problems that I know work. That would be the first thing. And then I would try to analyze the corresponding set. And if I hit a brick wall, I hit a brick wall. But that's how I would begin.
Thank you for the very interesting talk. So I was basically wondering about hallucinations, and like the way I think this learning theory works is that we want to get close to the global optimizer. But if you think about something like hallucinations, it seems to suggest that in certain parts of our input space, of our sample space, we are actually very close to what opt would return, but in others we are very far away. So is there any way that this theory can capture this?
So I can tell you what this theory can capture. It can capture situations where you have multiple minimizers. That works well. It's not exactly the same theory. It's much more complicated, but it can do that. Situations where you have a big part of your class are de facto almost minimizers, right? That it doesn't see. It doesn't. We didn't try to analyze this because up till very recently we didn't have an example where something like this could happen. When I think about it, I don't see any reason why theory can't be extended. But this is one of the things that until I write a proof, or at least see a way forward for a proof, I'm not going to bet anything about it. It's a very good question. I'm sorry I don't have a good answer.
And maybe one more question, which is like, I mean, in practice, people always care a lot about like performance on the training set, on the test set, and that's like super important. Whereas classical learning theory, it's just saying like, okay, we sample enough data, I find the right function, I'm happy. So do you think that, I mean, conceptually it makes a lot of sense, of course, from the optimization perspective, but do you think this is a limitation of the theory for our understanding what's happening in practice, or?
So I will be, I like to be very cautious, and although this is a theory I worked on for a big part of my life, I'm not married to it, and I'm not claiming that it would solve everything. Far from it. I don't see any fundamental difference because potentially if I know that if I work well on the training set and then I work well on the test set, it's almost equivalent to what I'm saying here, right? It's from a statistical perspective, it's the same. So I would say I think it should work, but again, it's one of the things that I want to write before I'm.
Thank you.
Thank you for the beautiful talk. I really enjoyed it. I wondered, you said in the beginning that it's kind of hard if you like go from like simple neural networks to like more complicated architecture. That a lot of the intuition, gut feeling, understanding of this kind of goes away. But I quite disagree with this. Like the transformer architecture is actually like quite intuitive and simple to understand. Like if you think about, okay, you have queries and keys and values and you want to transform them, like project them into a vector space where you can like focus on certain aspects. You do like a matrix multiplication, which is just like dot products of like queries and keys. You need to normalize because otherwise the dot products will kind of like just their scale will be different. You want them to like point in opposite directions if there's like a zero weight after the softmax because otherwise the softmax won't make this zero. So there's like a lot of gut feeling intuition that is actually rather intuitive like in a transformer to understand and maybe more so than a neural network. So I wondered like how much gut feeling about an architecture do we need to really kind of take that then into some theory and try to make progress there?
So one of the problems in this, the more subtle the questions are, the more the devil is in the details, right? And while the intuition works well, if you try to take the literature of classical neural networks, so say late 90s, and try to implement it based on what we know today, you will hit a few major brick walls. I'm on the one hand, I'm glad to hear what you're saying because it's a source of optimism, right? It means that maybe we're not as far, we are far, but maybe it's not an impossible task, and you just need to spend a bit longer trying to translate, etc. Which, by the way, is where working with people who actually do these things is incredibly important. I don't know of, for example, Peter Bartlett, who wrote that book. He sort of agrees with my statement, and he should know. I'm more cautious because I'm not really an expert on that facet. I would be very happy to discover that you're right, okay? And it's certainly worth the effort, but I can't predict how far it will take you.
Thank you.
Any further easier or difficult questions?
Thank you very much for your talk. So maybe I have a general question, because one of your points was the collaboration between different disciplines. So, and we know in machine learning that, of course, a lot of results came from statistical machine learning, computer science, and so on. And where do you see the main obstacles to collaborate between those communities, and why this is not working? So, or maybe it's working, but yeah.
No, it's not. Human psychology. For me, the biggest shock, and I say it as someone, I was a youngster when I discovered the shock, was that computer scientists and statisticians refuse to talk to one another. It's even worse than that. Today, I'm an editor-in-chief of a journal that's on, mathematical statistics and learning. And if someone from the statistical community, gets a paper that's written in a CS language, it's very difficult for me to convince that editor not to reject because the paper is annoying. Okay, and we're talking about now, it's not ancient history. So even the level of the language of sample complexity versus error rates, even that is, and that's totally human psychology, right? There's no scientific reason, because the two are equivalent. So I think that we as human beings, we like what we do, we're used to what we do, and we don't like it when people work on the same problems and do other things. There is no reason. I mean, I don't want to use this analogy, but if we view this as a Manhattan Project of our generation, then I think that some of these difficulties will disappear. But there is no deep fundamental reason why people from different disciplines shouldn't be able to collaborate if they want to invest the time and energy to do that.
Thank you.
So, in fact, if there's no further question, it's also a very nice kind of closing statement what you said, no? That in fact it is in our hands to work together, and I think you have shown also with your in your presentation that the universities still have here a lot to do to increase the understanding of the systems of today. Thank you for being here and for joining us for this presentation, and thank you also for the presentation and the talk.